Hello, welcome back. Today we're going to talk about entropy changes in chemical reactions or calculating delta S naught of reactions. So, first off, we need to talk about that little naught right there. That's our standard state, right? It defines a standard state. So, let's start by kind of reviewing these. Hopefully, we've seen these before, but maybe it's been a while. So, we're going to start off with that. So, standard states, if we have a gas, our standard state of a gas is 1 atm of pressure. All right, so we have 1 atm of pressure. If we have a liquid or a solid, we're just talking about its most stable and lowest energy state. So the key on that one, it'd be like carbon. We would talk about carbon being graphite. That's its most stable state and its lowest energy, right? Not diamonds, even though it is a standard state. But we're talking about that. And so the other things that we're talking about there is at 1 atm, just like above, and 25 degrees C usually because that's room temperature. All right. For substance in a solution, we're talking about 1 molar, all right, of a substance. And again, that's usually at 25 degrees C. Okay. All right. So our standard entropy change for a reaction is very simple. It's just like all the others, is where we take our final or our products minus our reactants. So we're going to take our products minus our reactants. This is what we did with delta H. We did this also with delta we'll do this with delta G and so delta S. So here's what we're looking at. We're talking about this reaction, or excuse me, that equation right there. We take the moles of the products minus the moles of the reactant. So it's very easy. We just kind of plug it in. All right. So that takes us to our third law of thermodynamics. And third law of thermodynamics states that the entropy of a perfect crystalline substance substance at 0 K or Kelvin is 0. So we're talking about we build up from there. So we're talking about at 0 K, right? Where all particle motion stops, the entropy of a solid is 0. And we go from there. All right. The next thing we need there is our trends in standard entropy. So as we talked about, gases tend to have higher than liquids and solids. All right, so that makes sense because we just have more places for them to move, more microstates, right? So gases tend to be higher because we have more microstates. All right. Most of the time, more masses equals more entropy. The book says it doesn't really want to get into it, but it's basically the fact that as these bigger molecules get closer to each other, there's more chance of movement, right? Or more chance of more microstates. And like I said, the book didn't get too depth into it. You really just need to know more massive, more entropy. All right, more chances, ooh, not changes, chances of microstates. All right, which leads us to our next word, allotropes. This was in your basic vocab, but allotropes are same forms, excuse me, same element. Let's say same element, different forms. Whoa, that was weird. Something broke on my pen. All right. Different forms of the same element. This would be talking about like carbon graphite. So carbon can be graphite. It can be carbon diamonds, right? We can also have like the Buckminster Fully. We can have carbon nanotubes. So there's kind of a lot of different options there. But our allotropes tend to be based on the structure, right? carbon diamond is going to be higher than graphite because diamonds are very rigid and structured. So it's going to take, carbon diamonds are going to be lower than graphite because it is so structured and rigid. All right, that's what we call anyone got the word? Ooh, a coordination complex. All right. Then we have molecular complexity. So generally, as the complexity of the molecule increases, the more complex it is. And that's because we have different um, layouts. We can have different layouts of the molecule. And remember, it's all about microstates. So if we have different layouts of the molecule, we are going to have more microstates. Because remember, our microstates is just a quick snapshot of each possible position that an atom or molecule can be in. All right. The next one, remember, dissolution is like dissolving of a substance, like dissolving a solid. And most of the time, this results in a higher entropy. All right. Increase in entropy. Now, real quickly, there are some exceptions, and I have seen the AP exam talk about an exception. They'll say, hey, this is an exception, explain why. And that's because when it dissolves, it actually becomes more ordered in the solution than it was in the compound, all right, or in our solid, okay, which is kind of rare, but it does happen. All right, so calculating standard entropy change, delta S naught for the reaction. So remember, we're taking products minus reactants. So really all we're doing is we're going to go back to the back of the book, the appendix, that thermodynamics one. Let me turn to my appendix here. We are looking at lots of answers. All right, we are looking at like appendix B. All right, so we can find this in appendix B. All right, and we have delta H, we have delta G, and we have delta S. Right now we're looking at the delta S's. And so what we're going to do is we're going to take delta S of our reaction is going to be equal to our product. So I like to do that just like I did with my other ones, right? 4 times NO, 6 times H2O, and yes, it does matter what state symbol we have there. Minus, we're going to have 4 times NH3 as a gas, and 5 times O2 as a gas. And most of the time, all of these are going to happen because we don't have anything at 0K. So they're all going to be just a little bit at some point. So let's start looking at our appendix in the back, right? So we'll start with our N's, right? We can go to nitrogen and find from there. So we've got NO gas is 218. That's not a 4. 4 times 218 point, how about 210? Ooh, good reading, Griffith. All right, 210.8 plus, do we have another one over there? Let's find this one while we're kind of in the N area. So we find ammonia, NH3 gas, 192.8. Okay, so we still need oxygen. And these all should be positive because, again, where there's 0 would be, that's right, you guessed it, at 0K, which we're not going to get there. All right, so now we can turn to, I think oxygen or water is going to be an oxygen area. So let's see if we can't find oxygen. Oh yeah, there we go. Water is, as a gas, we got 188.8. And then O2 gas, 205.2. 205.2. So we're ready to just do a little math here. I'm going to double check that first one, NO, because I feel like I might have, yep, 210.8. All right, so we're going to take 4 times 210.8. That's going to give us 843.2. I don't know what kind of brackets to put. Let's make our brackets more like parentheses. There we go. And we're going to add 6 times 188.8, and we get 1132.8 there. Minus, we got 4 times 192.8. We're going to go 771.2 plus 5 times 205.2. We're going to get 1026 there. All right, continue our math. So we're going to be subtracting 1797.2 here. And on this side, 1976. Whoa. Good, Griffith. All right. Minus 1797.2. Wow, that's real close. We're gonna get a positive 178.8. There you go. And remember, the label on this is going to be joules per mole dot K. Joule is the big key there, so we should get 178.8. And that is it. See you next time.